Hello everyone, this is Charlie F. Malabo, and this day we are going to tackle about the chemistry of water treatment. But before anything else, we should first know what is water treatment. Water treatment removes contaminants and undesirable components or reduces their concentration so that the water becomes fit for its desired end use. This treatment is crucial to human health and allows humans to benefit from both drinking and irrigation use. A water that can be consumed in any desired amount without concern for adverse health effects is termed a potable water. Potable does not necessarily mean that the water tastes good. This is in contrast to a palatable water, which is one that is pleasing to drink but not necessarily safe. The first step of water treatment is coagulation. The object of coagulation and subsequently flocculation is to turn the small particles of color, turbidity, and bacteria into larger flocks, either as precipitates or suspended particles. Technically, coagulation applies to the removal of colloidal particles. So why are colloids suspended in a solution and cannot be removed by sedimentation or filtration? Well, there are two reasons. First is the particles in the colloid range are too small to settle in a reasonable time period and too small to be trapped in the pores of a filter. Second, in order for the colloids to remain stable, they must also remain small. Most colloids are stable because they possess a negative charge that repels other colloidal particles before they collide with one another. In colloid destabilization, colloids are stable because of their surface charge. In order to destabilize the particles, we must neutralize this charge. Such neutralization can take place by the addition of an ion of opposite charge to the colloid. Coagulant is the substance or chemical that is added to the water to accomplish coagulation. And there are three components of coagulant, which are the trivalent cation, non-toxic, and insoluble in the neutral pH range. Trivalent cation is at the most efficient cation. The non-toxic is obvious for the production of a safe water. And last but not the least is the insoluble in the neutral pH range. So the coagulant that is added must precipitate out of solution so that high concentrations of the ion are not left in the water. And the most commonly used coagulants are the aluminum sulfate, ferrous sulfate, ferric sulfate, ferric chloride, coagulant aid, which consists of pH adjusters, activated silica, clay, and polymers. And the second step of water treatment is the softening. Softening is the removal of polyvalent cations from water that cause hardness. Hardness is primarily attributed to the divalent metallic cations, calcium and magnesium. When we say hardness, it is used to characterize a water that does not lather well or kanang dili kay mobula, causes a scum in the bathtub, and leaves hard, white, and crusty deposits or scale on coffee pots, tea kettles, and hot water heaters. The failure to lather well and the formation of scum on bathtubs is the result of the reactions of calcium and magnesium with the soap. So there are two types of hardness. One is the carbonate hardness. The second one is the non-carbonate hardness. Carbonate hardness is associated with carbonate and bicarbonate anions. It is defined as the amount of hardness equal to the total hardness or the total alkalinity, whichever is less. It is often called as temporary hardness because heating the water removes it. The second one is the non-carbonate hardness caused by ions that are associated with non-alkalinity anions such as chloride and sulfate. It is defined as the total hardness in excess of the alkalinity. If the alkalinity is equal to or greater than the total hardness, then there is no non-carbonate hardness. And non-carbonate hardness is also called as the permanent hardness because it is not removed when water is heated. Chemical precipitation of hardness. Precipitation of hardness causing ions has traditionally been accomplished by adding lime and soda ash to water. Soda ash may be omitted when the magnesium ion concentration is less 40 milligrams per liter as CaCO3 and when the non-carbonate hardness is insignificant. Ion exchange softening. Ion exchange can be defined as the reversible interchange of ions between a solid and a liquid phase in which there is no permanent change in the structure of the solid. Typically, in water softening by ion exchange, the water containing the hardness is passed through a column containing the ion exchange material. The hardness in the water exchanges with an ion from the ion exchange material. The next step of water treatment is mixing and flocculation. So when we say mixing, or also called as the rapid mixing, is the process whereby the chemicals are quickly and uniformly dispersed in the water. Ideally, the chemicals would be instantaneously dispersed throughout the water. So during coagulation and softening, the chemical reactions that take place is in rapid mixing form precipitates. So rapid mixing can be accomplished within a tank utilizing a vertical shaft mixer with within a pipe using an inline blender or in a pipe using a static mixer. Other methods such as partial flumes, hydraulic jumps, baffled channels, or air mixing may also be used. Flocculation. So while rapid mix is the most important physical factor affecting coagulant efficiency, flocculation is the most factor affecting particle removal efficiency. The objective of flocculation is to bring the particles into contact so that they will collide, stick together, and grow to a size that will readily settle. The next step of water treatment is sedimentation. Sedimentation, or the gravity settling, is the major unit operation used for removing suspended solids. Sedimentation is considered a unit operation or physical treatment involving solids liquid separation using gravitational force. Free settling. Free settling is observed when there are discrete non-flocculent particles whose size, shape, and specific gravity do not change with time as they settle. Particles settle as individual entities and there is no interaction between particles. Example of that includes the grit and sand particles in grit removal systems and plain sedimentation of surface water. Terminal settling velocity. The velocity reached by a particle as it falls through a fluid, dependent on its size and shape and the difference between its specific gravity and that the settling medium used to sort particles by grain size. So there are three forces that act on a particle as it settles. One is the gravitational force, the buoyant force, and the drag force. Another settling is the flocculant settling. Flocculant settling occurs in primary clarifiers and during settling of coagulated water and wastewater. As flocculant particles settle, their size, shape, density, and settling velocity will change with time. So, flocculant settling laboratory procedure. So, flocculant settling column analysis are typically performed in clear PVC column with sampling ports spaced approximately 6 inches or 15 centimeters apart. A column on the order of 5 to 6 feet or 1.5 to 1.8 meters is used. Ideal settling basin. Overflow rate serves as a design parameter used by engineers to determine the size of settling basins, whereas water treatment plant operators regulate the flow through the basin to maintain the proper detention time and overflow rate to achieve optimum solids removal. The basis for design of a settling basin is to select a specific diameter particle that will settle by gravity during the time that it takes water to travel through the basin. Another step of water treatment is the filtration. Filtration is a process for separating suspended or colloidal impurities from water by passage through a porous medium, usually a bed of sand or other medium. Water fills the pores or the open spaces between and sand particles, and the impurities are left behind, either clogged in the open space or attached to the sand itself. At most treatment plants, granular media filters are used. However, membrane process including microfiltration and um, ultrafiltration are now being used. So there are numerous ways of classifying filters, which are the gravity filters, filtration rate, slow and slow sand filters, rapid sand filters, and high rate filters or pressure filter. The last classification method is based on the type of media used in the filter. The single media or the monomedia filter, the dual media filter, and the multimedia filter. The single media or the monomedia filter have only one type of media, which is typically sand or crushed anthracite coal. The dual media filters is normally consisting a layer of coarse anthracite coal above a layer of sand. And the multimedia filter, such as the trimedia filters, consist of a layer of coarse anthracite coal above a layer of sand and a layer of garnet or ilmenite below the layer of sand. In depth filtration, it utilizes the thickness of cellulose-based media filter. This depth matrix is used to trap suspended particles, separating them from their carrying fluid. Surface straining or mechanical screening of suspended solids occurs when the particles being removed are larger than the pore space through which the water flows. Straining is the primary removal mechanism that occurs in slow sand filter or the slow sand filtration. Granular media filtration. The primary goal of granular media filtration is to use the entire filter bed for solids removal rather than being strained at the surface. Filter arrangement. So filters are typically placed adjacent to one another along one or both sides of a pipe gallery or gullet. The next step of water treatment is disinfection. Disinfection practice at water treatment plants has traditionally been the use of chlorine gas as the primary means of killing pathogens in water. Chlorine is both an economical and effective disinfectant. It is used in water treatment to reduce pathogens or disease-producing microorganisms to an acceptable level. Disinfection is not the same as sterilization, since sterilization implies the destruction of all living organisms, and drinking water does not really need to be sterile. So the primary goal of disinfection is to inactivate pathogenic organisms such as bacteria, protozoa, and enteric viruses that may be present in the water. Microbial pathogens of greatest concern are protozoan cysts associated with Giardia lamblia and Cryptosporidium parvum, and various enteric viruses which may be resistant to specific types of disinfectants. Chlorine reactions in water. So chlorine is the most common disinfecting chemical used. The term chlorine is often used synonymously with disinfection. Chlorine may be used as the element as sodium hypochlorite or as calcium hypochlorite. This reaction is pH dependent and essentially complete within a very few milliseconds. Hypochlorous acid is a weak acid and dissociate poorly at levels of pH below about 6. Between pH 6 and 8.5, there occurs very sharp change from undissociated HOCl to almost complete dissociation. Hypochlorite ions exist almost exclusively at levels of pH around 9 and above. Chlorine existing in the form of HOCl and or OCl2 is defined as free available chlorine. The chlorine disinfection involves a very complex series of events and is influenced by the kind and extent of reactions with chlorine reactive materials, including nitrogen, temperature, pH, the viability of test organisms, and numerous other factors. Such factors greatly complicate attempts to determine the to determine the precise mode of action of chlorine on bacteria and other microorganisms. The reactions of chlorine with ammonia are of great significance in water chlorination processes. When chlorine is added to water that contains natural or added ammonia, or ammonium ion exists in equilibrium with ammonia and hydrogen ions, the ammonia reacts with HOCl to form various chloramines which, like HOCl, retain the oxidizing power of the chlorine. So there are practices of water chlorination. Free residual chlorination. This free residual chlorination practice involves the application of chlorine to water to produce, either directly or through the destruction of ammonia, a free available chlorine residual and to maintain that residual through part or all of a water treatment plant or distribution system. So when free available chlorine residual is desired, the characteristics of the water will determine how it can be accomplished. First, if the water contains no ammonia or other nitrogenous materials, the particles of chlorine will yield a free residual. Second, if the water does contain ammonia that results in the formation of a combined available chlorine residual, it must be destroyed by applying an excess of chlorine. Another common disinfectant is the chlorine dioxide. It is formed on site by combining chlorine and sodium chloride. It is often used as a primary disinfectant in activating the bacteria and cysts, followed by the use of chloramine as a distribution system disinfectant. It does not maintain a residual long enough to be useful as a distribution system disinfectant. But the advantage of chlorine dioxide over chlorine is that chlorine dioxide does not react with precursors to form DBPs. Also, chlorine dioxide is a very strong oxidant. When chlorine dioxide reacts in water, it forms two byproducts, chlorite and to some extent chlorate. These compounds may be associated with a human health risk, and therefore many state regulatory agencies limit the dose of chlorine dioxide to 1 milligrams per liter. Also, it is also been associated with tastes and odors in some communities. The health concerns, taste, and odors, and relatively high cost have tended to limit the use of chlorine dioxide. So, ozonation. Ozone is a pungent smelling and stable gas. It is a form of oxygen in which three atoms of oxygen are combined to form the molecule O3. Because of its instability, it is generated at the point of use. The oxygen in the air is dissociated with the impact of electrons from the discharge electrode. The atomic oxygen then combines with atmospheric oxygen to form ozone in the following reaction. Next is the ultraviolet radiation. So ultraviolet light disinfects water by rendering pathogenic organisms incapable of reproducing. This is accomplished by disrupting the genetic material in cells. The genetic material in cells, namely the DNA, will absorb light in the ultraviolet range, primarily between 200 nm and 300 nm wavelengths. The second to the last step of water treatment is the adsorption. Adsorption is a mass transfer process wherein a substance is transferred from the liquid phase to the surface of a solid where it is bound by chemical or physical forces. So the adsorption with PAC or the powdered activated carbon is added for the removal of taste and odor compounds and the removal of organics. It may be added at the intake prior to rapid mixing at the rapid mixer or filter influent. Better treatment occurs by providing longer contact times so that equilibrium conditions can be reached. The PAC or the powdered activated carbon is fed either as a powder or slurry using metering pumps. The adsorption with GAC or the granular activated carbon is sometimes used as pre-filtration adsorption ahead of conventional filtration, but primarily as a post-filtration process, since it is more effective at this stage because much of the turbidity and organic constituents have already been removed. GAC, or the granular activated carbon, has been used to retrofit conventional sand filters. Existing filters can be converted to GAC filter adsorbers by replacing a portion or all of the existing media with GAC. The last step of water treatment is the membrane. A membrane is a thin layer of material that is capable of separating materials as a function of their physical and chemical properties when a driving force is applied across the membrane. In the case of water treatment, the driving force is supplied by using high-pressure pump, and the membrane type is selected based on the constituents to be removed. So membranes can be described by a variety of criteria including membrane pore size, molecular weight cutoff, membrane material and geometry, targeted materials to be removed, type of water quality to be treated, and or treated water quality. There are two categories of membrane processes, which are the pressure-driven and electrically driven processes. But in this discussion, it is limited only to pressure-driven membrane. That includes, first, the reverse osmosis. This process has traditionally been employed for the removal of salts from brackish water and seawater. The second is the nanofiltration. This process, also called as the membrane softening, lies between the reverse osmosis and ultrafiltration. The third one is the ultrafiltration. The ultrafiltration membranes cover a wide range of the MWCOs and pore sizes. And the last one is the microfiltration. A major difference between microfiltration and loose ultrafiltration is membrane pore size. The pores of microfiltration are approximately an order of magnitude greater than those of the ultrafiltration. And the primary application for this membrane process is particulate and microbial removal. So that would be the last step of water treatment. Thank you for watching.